The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so today we're going to talk about RKR and a few other things. Before I start, though, I want to refer you to two wonderful documents that are produced by Bob Leroy, and you can get them at his website. And the two that I have here, one is a program called, is a document called RKR1. I don't know whether it's RKR1 now, because this is dated 1992, but it is the definitive RKR program, and you can download it. And whatever, it contains a write-up of what the RKR is, which is nominally the purpose of this lecture, but also it's a program that works. And there's also a thing called level. And level, among other things, starts with the potential and calculates the vibrational wave function and anything else that you would calculate from expectation values or overlaps of vibrational wave functions. And again, this is the definitive numerical integration routine for diatomic molecules. And so these are two incredibly important tools in diatomic molecule spectroscopy. And Bob Leroy really owns them. And there are a couple of other areas that Leroy is the key person. And so it would be a good idea to obtain these documents. And in previous years, I would always assign some kind of a problem where you would have to use both of those programs. And I don't have the heart to do that this year, so I'm just going to say, look at them and maybe use them. Okay, so you have approached the energy levels of diatomic molecules using perturbation theory. And part of the reason that I spent a lot of time on this kind of perturbation theory treatment is that everything you do using perturbation theory on diatomic molecules transfers to polyatomic molecules. There is an exact procedure for relating the energy levels to the potential energy curve in diatomic molecules, and that's called RKR. And that does not transfer to polyatomic molecules. So it's a little bit of a bait and switch if I were to tell you only use RKR because it works and is wonderful, because you won't be able to take it over. And so that's why I invested so much in perturbation theory. Now, one reason you would not just use perturbation theory on diatomics is because they're not accurate enough. You really want to represent all observable properties and relationships between them as accurately as possible through one common thing, and that is the potential energy curve. And if you use perturbation theory, you make a good approximation to the potential energy curve near the bottom. And the higher up you go, the more you don't really know how good it is what you've built. Okay. So RKR, Rydberg-Klein-Rees, is a direct product of WKB, Wenzel, Kramers, Brillouin. this is a semi-classical approach. It is a fantastic thing, fantastic tool, and it is relevant, at least in little bits of analysis for polyatomic molecules. You are able to determine the shape of the wave function, qualitative features of the wave function, without solving a Schrodinger equation. So basically, all you need to know is what is the kinetic energy at a particular point in space. Now, that's not a quantum mechanical idea. That's a quantum mechanical impossibility. But classically, you can ask, well, what is the momentum anywhere in space, or what is the kinetic energy? And now, for a diatomic molecule, kinetic energy is a scalar quantity, momentum is a vector quantity, and one can ignore the fact because there's only one direction. But in a polyatomic molecule, what you really want is momentum, and that's a vector quantity, or and what you have really is the distance of your the energy above the potential surface, and that's a kinetic energy. And so you have to be careful. But let's look at WKB for a little while, because this is such a wonderful thing. Okay. So semi-classical means that we can define momentum classically, and this is not the quantum mechanical momentum, but it's a function. It's a perfectly legitimate function. We could calculate expectation values of it, but the momentum is well, the kinetic energy is p squared over 2 mu, right? This is the reduced mass, and so to get p, you have 2 mu e minus v of r. So that's the classical momentum function. The WKB wave function, which you can derive by making some clever expansion where basically you get quantum mechanics, classical mechanics if h is 0, and you get quantum mechanics otherwise. The WKB wave function has this minus a half. Okay, so this is an envelope function, and this is the oscillatory function. Okay, and this is a turning point, so you're integrating this classical momentum function in from a turning point to where you want to look at the wave function. And the larger this p is, the faster this exponential wiggles. And if you have functions that are oscillating rapidly, and you have integrals involving functions that are oscillating rapidly, the only place where the integral accumulates is where the two things are oscillating rapidly at the same frequency. And so this is an extremely important thing because it gives you causality. It gives you, this is where something is, if you're using these kinds of wave functions and you're calculating the expectation value of something, you can think that the expectation value of something is due to something that occurred in a particular region of space. And this is the way we think about the classical world. And so this oscillatory thing is amazingly important because it gets you back to classical mechanisms. And you've heard of, I won't talk about that. And this is the envelope. So the faster something is moving, the smaller this factor is. And again, that comes out of a probabilistic idea. If something is moving fast, it doesn't spend much time in a particular place, and you can actually work out what the envelope function ought to be based on calculating, okay, suppose you have, we have motion in a potential. If you can calculate what the period of oscillation is, and you can calculate, say, how long it takes to go through a particular region of space. If you know the momentum at that point, you can calculate how long it takes to go through this. And the ratio of that time to the period, or to half the period, tells you the probability of finding the system in this point, in this region. And so the probability is proportional to 1 over the momentum, and the probability amplitude, which is what the wave function is square root of that. So we have something that it tells you what is the probability of finding a system in a particular region of space and how it oscillates. And these two are enough to build an incredible amount of insight. Okay, so now we have a problem that we're at some energy, and we have a wave function, the WKB wave function, which it turns out is valid away in a region of space not near a turning point. Because at a turning point, the momentum is 0, and this blows up, and that's unphysical. And so if we wanted to use WKB to describe energy levels, we have a little bit of a problem. We're okay outside in the non-classical region of the potential. And, but in the non-classical region, the wave function has to go to 0 at infinity, and that's a boundary condition. And we're okay inside, but we have wave functions propagating inside, and they have to meet and be, and where these two wave functions meet, the wave function has to be continuous. And so, okay, first of all, the way you deal with this gap at the boundary is that you discover that you can approximate this region here as a linear potential if you're close to it. And then you have wave functions that are, well, they're Airy functions. Airy functions are the correct wave function for a linear potential. And so with Airy functions, you can go across this region, and you join up these two things. The wave function having to go to 0 at infinity, positive and negative infinity, imposes a definite phase. And what you end up discovering is that the wave function at a point where the WKB is valid on the inside of the potential is the WKB wave function you would have calculated from here, but it's not valid here, plus pi over 4 with a phase of pi over 4. So it's a long, complicated lecture explaining how you join the wave function. You get the correct wave function. And joining across the boundary is a really important piece of that. I won't do that. Then the continuity, that leads to what's called the quantization condition. because the only way wave functions which go to 0 at infinity correctly can be legitimate solutions is if the two wave functions are continuous and the derivative is continuous. And so you end up getting a quantization condition, and the quantization condition is I'm going to put the so this is the quantization condition. This is an integral. This quantity is. Did I blow a sign? No, that's right. This is the classical momentum. So it's an integral p dq or pdr. This pq has the dimension of h. It's also a quantity that is known as action. Now, a personal story. I was an undergraduate at Amherst College, and we all write theses, and we have a thesis defense. And at my thesis defense, Dick Fink, who was a young assistant professor at the time, asked me a question, which was, what is the unit of h? And I said, energy times time. And I was right. But he didn't want that. He wanted action. And we went around for half an hour. I was absolutely certain that I knew what the units of h were. And he was determined to get action. And we never converged. But anyway, this is an action integral. And basically, the quantization condition says there's a certain allowed amount of action that at each energy level, the action integral is an integral number of. So if we kill so if we make this just h over 2 to v plus 1, or h times v plus a half. That looks a little more familiar. So there's a half integer amount of action when you evaluate the action integral at the energy of an energy level. And there's also, you get for each additional level, there's another h of action. And so this is a very useful quantity, and the RKR is built on the action integral. Okay, so the derivation of the RKR method is mathematically opaque, especially when I have to present it in a lecture. And there are many different ways of motivating it. They all say, let's start with some function of energy and rotation. And these lecture notes were written in 1975 and revised over the years. My book was written in 2004, sorry, and it's better in my book. And I don't know why I didn't do this earlier. So we can describe this function by the quantity that appears on as, where is it? Equation 22 on page 4. So we can just define A as this function, 2 mu over h bar squared square root 1 over I r minus r plus. And these are functions of energy. E minus u of r minus h bar squared over 2 mu r squared jj plus 1 dr. Okay, so this, what is this? This here is the centrifugal potential. This is V of J of R. Okay, this combination. And so you have the bare potential and you have the centrifugal correction. And so this difference is the energy. So if we have the potential like this, and this is the energy, A is just the area. That's why it's called A. Now there's some other stuff to make it dimensionally consistent. So we have a function that we are going to play with two different ways. One way gives us r minus and r plus at E. So if we knew what A was, then we could do something and derive values for the turning points from it. And the other way of processing this is to find out what A is based on what we know from spectra, which are the vibrational and rotational constants. So we determined this from the spectrum. G of E is, omega E, V plus a half, et cetera, and this is BE minus alpha E, V plus a half, plus whatever. And so we take this thing and we approach it two different ways. One gives us turning points, if we knew that, and the other gives us that if we knew this. So this to that is where we want to go. Okay, Bob Leroy says that the best way to learn about RKR is to read Klein's paper, probably in German, from 1932. And that he says also that there's a paper by Kirshner and Watson. This is Jim Watson, who is as close to God in spectroscopy as you can get. He says that this was de-discovered. In other words, Watson and Kirshner wrote basically Klein's paper again in 1992. And so it might be almost as good to read the Kirshner and Watson paper. But anyway, and Leroy does not like the way I developed this by saying, okay, let's consider this function and process it two different ways. But I've been doing this all my life, and I'm just unable to escape that. Now, given this function, it's an exceedingly easy thing to make the connection between this and that. That's a couple of steps. The other thing of showing how you can build these two things in to determine that is mathematically tedious and involves all sorts of stuff. And I'm not going to do that. But the lecture notes do that. Okay, so let's just take a look at this function. And suppose we take the derivative, the partial derivative of A with respect to E. Okay, so we get all sorts of garbage out in front. And now we have an integral, and so we're going to take the derivative, and this isn't e, that's e. That we take the derivative, that's 1. So we get the constants out in front, and then we have integral r plus r minus of e r. That's a pretty easy integral. Even I can do that one. And so that gives us this constant times r plus of e minus r minus of e. So the first integral, or the first equation, we get the derivative, this derivative of this area, it just gives us the difference in turning points, which is a nice thing. Okay, and now let's look at the partial derivative of a with respect to j. Well, where's j? J only appears here. So these two terms go away, and we get 2j plus 1 times that. So we get all that constant stuff, and we have an integral, and we can take minus h bar squared over 2 mu out, and we can take 2j plus 1 out, and we have now the integral from r minus to r plus of 1 over r squared dr. And this gives us, this integral gives us 1 over, so this is equal to minus 1 over r plus minus 1 over r minus. Right? I'm very bad at integration, even something simple like this. So we have minus sign canceling that, the minus sign I took out here, and we get now an integral that involves, so we have one integral that's the difference in the difference in turning points at E, and this is the difference in the reciprocal of the two turning points at E. Two unknowns, two equations, bam, you've got it. And so if we can know A of EJ, we can determine the turning points R plus of EJ and R minus of EJ. And that's what RKR is. Okay, so I won't go through the derivation because I don't like it. It's tedious. It involves a change of variable and integration by parts and all sorts of stuff that you can do. And you wouldn't want to see that on a blackboard from someone who is uncomfortable doing it. And so what you discover is that R plus minus R minus is equal to 2 h bar squared over 2 mu square root integral over the vibrational quantum number that's J. So the difference in two turning points is given by at E, and E can be treated as continuous. This is the inversion of E of V, and so this can also be treated as a continuous function. So you can determine R plus minus R minus as a continuous function of V if you know G of E. or a continuous function of E. So this is one thing. And so you do that. And you can have something like this from polyatomic molecules too. So what is this doing? It's telling you what is the width of the potential. And that's mostly what you want to know. It would be nice to know where this is and where this is. But the difference between them is the most important thing, because often you're willing to say, I'm going to use a model. Not a model that's completely free, a model that is saying what is the qualitative form of the potential, and the difference between the two turning points is all you need in order to pin down the model. And that could be done for polyatomic molecules. One of the problems is, what is the potential? What are the coordinates? Because you are observing energy levels. They're energy levels, or they're levels in state space. There is nothing about the coordinates. And so there's all sorts of problems of saying, okay, well, we would like a one-dimensional cut through a potential surface. But there's all sorts of issues of, well, yeah, we could determine the width of the potential along some one-dimensional cut, but we don't know what the coordinates are. So this is interesting, and it's kind of an area where some insight might be gotten for polyatomic molecules. Okay, and the other one is 1 over r plus minus 1 over r minus. And that's, again, we got this same kind of stuff. I don't know whether, except the 2 over 2 mu or h bar squared, square root. And now we have so here is an integral involving a combination of the rotational constant function and the vibrational energies. And again, if you know these functions, and you can pretend that they're a continuous variable, a continuous function of v, it's determined point-wise, but so you can determine this integral at any energy, and so you have this difference of turning points at any energy, and so between the two you've got it. Now this is why you can't even think about using this for polyatomic molecules, because this is the rotational constant for a one-dimensional oscillator, and for a polyatomic molecule you have 3 rotational constants. They're all a function of displacements. They're all affected in different ways by displacements along normal coordinates. You can take derivatives of the A, B, and C, or the inertial constants in the A, B, and C directions, and so you can show how the rotational constants would change with respect to vibrational excitation, but you can't do something like this. There is no sensible way. Yes?
What if you have like acetylene where there is only one rotational constant in ground state?
Yes, but you still have 7 vibrational degrees of freedom, of which, and so what potential are you sampling? Okay. So you can sort of do this. You can't do that. This might be useful. Okay, now, there are all sorts of issues with these kinds of functions. At the upper turning point here, the energy is equal to the vibrational energy. And so this is 0. The integrand goes to infinity. And so there's a singularity in this integral at the upper limit of integration. No problem. But it's something people worry about. But there is one thing that happens very commonly when you do RKR. You generate a potential curve that instead of looking like this, looks like that. The inner wall tends to hook, and this is a common problem, and it comes from blindly using BV and G of V. Keep in mind that you're determining the outer wall is moving very fast. So you're sampling the energy levels, and the outer wall is changing its position rapidly with V. The inner wall is mostly going up slowly. I mean, it's going up vertically, not changing much. And so all of the RKR is being stressed by trying to determine this rapidly changing function with perhaps incomplete, perhaps defective data, and you almost always get a hook. And so what you do is you say, okay, what is the functional form for the inner wall? And you constrain the RKR to have the right inner wall, and that gives better potentials. There are other things that people do to improve on RKR potentials, but one of the best tests is, okay, we have V of R, and we automatically get the J dependence of it. And so we should be able to calculate from it G of V, B of V, D of V, and many other things. And now, RKR used G of V and B of V to determine this. But we have the potential, now we do numerical integration of the, we solve for the, you have a potential, you find where the energy levels are, not by semi-classical methods, but by integration of the Schrödinger equation. And so you can then solve the problem by numerical integration and ask, well, do the calculated values of quantities obtained from the potential, are they equal to the input values? It's not a circle. If you are using semi-classical methods to get this, and strictly quantum mechanical numerical integration methods to invert back to the spectrum. And the agreement is astonishing. And so that's an important characteristic of RKR. It works. It's a trivial program. Even in 1970, it took seconds to run. And on a big computer. But big computer, in those days, yes, they were pretty slow. Whereas Frank Condon, or the numerical integration, takes hundreds of times longer. Now, both take no time at all on your laptops. So it's a wonderful procedure, and it makes using models in diatomic molecules completely stupid, unless you have essentially no data and you want to take a little bit fragmentary data and get a little bit of leverage to extrapolate or interpolate, hoping to find more so that you can verify things. But the RKR is just a wonderful thing. And often you see people still writing papers questioning the validity of RKR potentials and saying, well, you really ought to take this to a higher order of WKB, and you can do that. And in fact, that's built into Leroy's programs. So it's not time to quit yet, but
it's time for you to ask a question.
Yes.
So WKB wave functions are harmonic.
No.
No?
Why do you say they're harmonic?
Well, so by the way, if you have a harmonic potential,
Yes.
you'll be exactly right.
It turns out that WKB is invalid near turning points.
Right.
At the bottom of the potential, V equals 0, you've got two turning points close together. So you say, well, if there's ever going to be a problem, it's going to be here. However, near the bottom of every potential, it's a good to very good approximation. It is harmonic. WKB works everywhere for harmonic oscillator. There is no...
Right. Oh, okay. So that's kind of what I
Yeah.
meant, right? But at very high excitation, you have enormous anharmonic contributions from a real potential.
As long as the potential doesn't have kinks or is not double valued, you're okay. I mean, this RKR does not give you the correct energy levels for this sort of a problem.
But it has nothing to do with WKB.
Right. No, that.
Right.
Sure. But RKR is scarily correct for very anharmonic, like Morse potentials.
It does absolutely. You know, the scary point is down here. Everything else, you know, as long as there's no twiddles, it's valid. The higher you go, the better it is. That's another thing about semi-classical. The higher you go, the closer it approaches semi-classical. Yes. So the problems with RKR, this one, is the most commonly encountered. And it's not a problem with the semi-classical method. It's a problem that you're trying to determine a very rapidly changing function with incomplete data. And it doesn't know any difference between inner and outer turning points. It just pulls, it nails the difference, but the rotational constants are what's determining the absolute positions, and that just gets overpowered. So are there other questions? Should I come up with a problem that forces you to use the Leroy's programs? The problem that I've discovered in asking people to use Leroy's programs is Leroy writes programs in Fortran, which is the only language that I understand, and nobody knows Fortran anymore. So that makes for terrible difficulties in using his program. However, in these publications, he gives detailed discussion of the structure of the input files and the output files. And so basically, you can use them as a black box as long as you believe in RKR, which I think is a very, there are many other things that you would not want to believe in. You can pretty much take it for granted. So I urge you all to download these things and have a functioning numerical integration program and an RKR program in your computers, and it would be a good idea to do something with them, but I'm not going to ask you to hand it in. It might be a good idea to look at the paper by Mance and et al. That I cite in the notes, and take the data set that he uses and just reproduce his results to show that, yes, in fact, it does reproduce B of V and G of V to the accuracy to about a part in 10 to the 6th or maybe part in 10 to the 8th.
What paper do you, Mance and the...
Yeah, that Mance et al., that's actually Mance, et cetera, is there. And so I recommend doing that. And if that's it, then I'm done.